You know that moment, right? You're driving along, maybe listening to something, and then bam, flashing lights. The gates start coming down. That distinctive sound of a railway level crossing.
Yeah, that pause.
Exactly. And there's that split second, do I stop or, and then the train just roars past. It's like such a common thing.
Mm-hmm.
But have you ever stopped to think, how do we actually figure out how safe these things are, these critical intersections?
It's a good question.
Yeah. Like, how do they decide, okay, this one needs barriers, this one just needs lights, and, how safe is safe enough? Because perfect safety isn't really possible, is it?
Not entirely, no.
So today, that's what we're doing, a real deep dive into these pretty sophisticated methods they use to analyze the risks at level crossings.
Right.
It's not just about, cars and trains not hitting each other. It's about understanding this fundamental clash, two totally different transport systems meeting, and the advanced math that goes into making these points as safe as they possibly can be.
It really is a fascinating challenge and complex because you're not just modeling like concrete and signals.
Right.
You're trying to model human behavior, which is notoriously tricky, plus the technical systems, environmental factors. It all feeds in.
So what are the main goals when you apply risk analysis here?
Well, generally, there are two big ones. First, you've got to choose the right type of protection for that specific crossing, what tech fits best.
Yeah.
And second, you need to set really precise technical safety targets for the folks actually designing and building those technologies. Like, how reliable does this piece of equipment have to be?
Got it. Okay, so let's unpack the core problem first. What makes level crossings such specific hazard points? I mean, it's just where a road meets a track, right?
On the surface, yeah.
Yeah.
But the fundamental issue comes down to the completely different safety philosophies of road versus rail traffic.
How so?
Think about driving your car. You've got rubber tires on tarmac.
Okay.
Pretty good grip, right? High adhesion.
Sure.
So you can brake relatively quickly. You can swerve around something if you need to. Road safety relies a lot on rules, driver behavior, reactions.
Makes sense. And car safety features.
Often focus on passive safety, yeah. Things like airbags, seat belts, stuff that reduces how bad an accident is if it happens.
Okay. And trains.
Totally different world.
Yeah.
Steel wheels on steel rails, very, very low adhesion. Which means trains need way longer distances to stop. Huge distances. And they're on tracks, obviously, so they can't just swerve out of the way.
No quick dodging.
Exactly. So rail safety depends heavily on technical systems signaling interlocking to prevent incidents in the first place. It's all about active safety, avoiding the accident altogether.
Okay, so here's where it gets interesting for you listening. These two very different approaches, they just collide head on at a level crossing.
Precisely. The design has to be smart enough to make sure that road users, with all their potential errors, don't compromise the railway's safety systems. But also that the train's characteristics, like those long braking distances, don't make it unreasonably dangerous for cars. It's a real balancing act.
A tightrope walk, you said.
Yeah.
And you have to factor in driver error, right?
Right.
Because people make mistakes.
Absolutely critical. You simply have to account for road user errors in the design because you can't eliminate them entirely unless you, get rid of the crossing completely, build a bridge or tunnel.
Which isn't always feasible.
Not always, no. And the most severe risk, obviously, is that collision between a train and a road user.
Yeah.
And the statistics are pretty grim. Globally, on average, about one road user is killed in every fourth collision. It's stark.
Wow. That's sobering. Are there other risks?
Yeah, definitely. There are less severe events, but still important ones, like cars hitting the safety equipment, barriers, or even road users hitting each other on the crossing due to congestion or confusion. All that still factors into the technical safety requirements.
And what's the main cause behind the really bad ones, the train vehicle collisions?
Overwhelmingly, it's road user behavior. Somewhere between 80 and 90% of collisions.
80 to 90%.
Yep. And we usually think about these errors in two ways. Intentional ones, like someone trying to beat the barrier, and unintentional ones, like just not seeing the signals properly.
Okay. And where do these tend to happen?
You can think of two main zones. There's the approach and decision zone, so that's before you get to the crossing. That's where someone might miss the warning or sometimes deliberately ignore it.
Right.
And then there's the clearance zone, which is the area on the tracks themselves. Here, the big risk is often the traffic environment, like getting stuck in a traffic jam right on the crossing.
A nightmare scenario. So if human behavior is the big elephant in the room, how does technology try to manage it? You mentioned different types of crossings.
Broadly, yeah. You've got passive crossings, which have basically no tech, just signs, maybe markings. It's entirely up to the road user to look and listen for trains. And then you have active crossings. These are the ones with technical gear lights, bells, barriers that actively warn users when a train is coming.
And these active ones are where the real engineering comes in, I guess.
Yeah, definitely. They get pretty sophisticated.
Huh.
We categorize them based on several things. First, the type of protection. What does the driver actually see? Is it just flashing lights? Lights with half barriers that block one side of the road? Or lights with full barriers that block the whole thing?
Gotcha.
Then, the type of activation. How does the system turn on? Is it automatic, triggered by sensors detecting the train? Is it integrated into the main railway signaling system, the interlocking? Or is it sometimes activated manually by railway staff?
Okay. What else?
There's the type of supervision. How does the system know if something's gone wrong, if there's a malfunction? Are there special railway signals involved? Does it depend on the main train signals? Or is it supervised remotely from a control center?
And one more.
Yep, the type of monitoring of the danger zone. This is about checking if the crossing itself is actually clear of obstructions. Again, could be automatic sensors, could be someone watching via camera, or even direct line of sight.
So many types. Can you mix and match all these?
Not entirely. They're often linked. For example, if you have automatic monitoring to check if the crossing is clear.
Like sensors.
Yeah, like sensors or radar. You usually need good signal supervision too, so you can reliably tell an approaching train to stop if the system detects an obstruction. They have to work together.
Right, that makes sense. Okay, so let's dig into the first big application you mentioned. How authorities actually pick the right protection for a specific crossing. This is where the risk analysis really kicks in to spend money wisely, right?
Exactly. Efficient use of resources is key. It's typically this iterative 4-stage process.
Okay, walk us through it.
First stage, hazard identification. Basically, brainstorming everything that could possibly go wrong at that particular spot. You list it all out systematically. Then stage 2, risk analysis. This is where you start putting numbers on things. You quantify the parameters to actually calculate the level of risk.
The calculation part.
Yep. Stage 3 is risk assessment. You take your calculated risk number and compare it to some kind of acceptance criterion. You decide, is this risk acceptable or is it too high?
Defining safe enough.
Pretty much. And if it is too high, you move to stage 4. Risk control. This is where you implement measures to bring that risk down. Maybe upgrade the equipment, maybe add warnings.
And then you cycle back.
You might have to, yeah. You reassess the risk with the new measures until it meets the acceptable level. It's a continuous loop.
Got it. And you mentioned calculation. At the heart of that risk analysis stage, there's a formula, right?
There is. The classic definition of risk, R, is the frequency, F, of something bad happening multiplied by the severity, S, of the outcome. So RR equals FXS. Simple idea.
Simple idea, but I bet it gets complicated for level crossings.
It does. That frequency part, F, gets broken down further into 3 key factors for level crossings.
Okay, what are they?
First, there's exposure. E. Think of this as how often, theoretically, a car and a train would arrive at the crossing at roughly the same time if there were no warnings or barriers at all.
Just based on traffic volume and timing.
Exactly. Second is hazard H. This is the probability that, given that theoretical simultaneous arrival, the safety measures fail to prevent a dangerous situation. Often, this is linked to human error. Someone ignores the signal, drives around the barrier.
Okay, the chance the protection doesn't work as intended, including the human part.
Right. And the third factor is unavoidability. This is the probability that if a hazardous situation occurs, like a car on the tracks when the train is coming, an actual accident cannot be avoided.
So even if there's a hazard, maybe someone slams on the brakes or floors it.
Potentially, yeah. So putting it all together, the full formula looks like risk, R equals exposure E times hazard H times unavoidability U times severity S.
R, E, X, Q, X, S. Okay, let's break those down. Exposure E first. You called it theoretical strikings per time unit. Now, my first thought is more cars, more trains means more exposure, more risk. Simple linear thing.
Yeah.
But you mentioned something counterintuitive, the traffic jam effect.
Ah, yes. This is really interesting. It's not strictly linear. High road traffic intensity can actually reduce exposure sometimes.
Wait, what? How can more traffic reduce the chance of a car and train being there at the same time? That sounds completely backward.
It does sound backward, but think about it. If you have really heavy road traffic and the crossing protection activates the lights flash, the barriers come down.
Traffic backs up.
Exactly. A queue forms pretty quickly. This means fewer vehicles actually reach the danger zone on the tracks before the train arrives, compared to a situation with lighter, faster-moving traffic where more cars might slip through just before the warnings start.
Oh. So if you just assumed more traffic always equals more exposure, you'd actually overestimate the risk on very busy roads.
Precisely. Neglecting that traffic jam effect can lead to significantly overestimated risks, especially for high-volume road crossings. It's a crucial detail.
Okay, mine's slightly blown. What about hazard? H. Hazards per theoretical striking. This is about the protection failing, often due to people, right?
Yeah, it's the probability that road users basically deviate from the plan, they don't react correctly to the warnings. And this value, H, is heavily influenced by the type of protection installed.
Give us some numbers. How much difference does the tech make?
It's dramatic. For a passive crossing with no active warnings, the hazard probability, H, is roughly 10 to the minus 1. So 1 in 10 theoretical simultaneous arrivals becomes a hazardous situation.
Okay, 1 in 10.
Add flashing light signals, and it drops to about 10 to the minus 2, 1 in 100. Add light signals and half barriers, it goes down to about 10 to the minus 3, 1 in 1,000.
Much better.
And with light signals and full barriers that block the whole road, it plummets to around 10 to the minus 5. That's 1 in 100,000 theoretical strikings becoming a hazard.
Wow. That's a massive difference. Really shows how barriers prevent those deliberate errors.
It clearly demonstrates the effectiveness of different technologies in mitigating that human error component.
Okay, next up, unavoidability.
Yeah.
Accidents per hazard. So a hazard happens, but maybe you still avoid the crash.
Potentially, yes. Not every single hazard leads to an accident. A road user might react just in time, brake hard, accelerate clear, maybe even swerve slightly if there's space.
But the train driver.
Usually the train driver can't do much, unfortunately. Those braking distances are just too long. So unavoidability mostly depends on the road user's ability to take evasive action. And the key factor there is visibility.
Weather conditions, time of day.
Exactly. If visibility is practically zero dense fog, say avoiding is pretty much impossible. U is close to 1. Every hazard becomes an accident.
Makes sense.
With medium visibility, maybe it's possible sometimes. Might be around 10 to the minus 1, so 1 in 10 hazards results in an accident. With really good visibility, clear day, drivers might avoid it more often. Could be down around 10 to the minus 2, 1 in 100.
So good visibility gives the driver a fighting chance, even if they made an initial mistake.
A small fighting chance, yes.
Okay, last piece. Severity S. Weighted personal injuries per accident. How do you quantify that?
We use a weighting system to compare different outcomes. A common standard is 1 fatality is considered equivalent to 10 serious injuries, which is equivalent to 100 slight injuries. This gives you a single weighted injury number per accident.
And what influences severity the most?
Railway speed. It has a very strong, almost linear relationship with severity. Faster train, much worse outcome.
Is there a formula for that?
A typical one used in these analyses for, say, passenger vehicles might be S.00024 times the train speed in kilometers per hour.
So double the speed, roughly double the severity score.
Roughly, yes. It's also worth noting pedestrians usually face the highest severity for the same train speed just because they have no protection around them.
Grim but logical. Okay, so we have R, X, H, X, U, X, S. We calculate R. Now what? The risk assessment part.
Right. You have your calculated risk number. Now you need to decide if it's acceptable. And since you can't get risk down to absolute zero...
You need a threshold. Recept it.
Exactly. An acceptable risk threshold.
Right, yeah.
For accepted, that's greater than 0. And choosing this threshold is tricky.
Why tricky?
Because it's not just a technical decision. It involves legal aspects, ethical considerations, sociopolitical factors. How much risk is a society willing to tolerate? And importantly, those standard technical safety criteria you might use for, say, a purely automated system.
Like the RACTS you mentioned earlier.
Right. They don't work so well here because of that huge factor of intentional human violations. People deliberately breaking the rules is hard to fit into standard technical risk models.
So how do you set that acceptable risk threshold?
There are a few approaches. One is looking at historical data. What was the average risk level across similar crossings in the past? The idea is not to let future risk exceed the historical average.
Okay, benchmarking against the past.
Another way is using benefit-cost analysis, weighing the cost of safety measures against the reduction in risk. Or using purely theoretical scenarios.
Is there a typical number?
Well, as an example, studies in Germany looking at data from 2009 to 2013 established an average accepted risk of about 0.0002 weighted personal injuries per level crossing per year. That became their working benchmark.
0.002 per crossing per year. Okay, so if your calculated R is higher than that.
Then you move to risk control. Measures are needed. You have to do something to reduce the risk.
Likewise.
Could be major, like closing the crossing and building an overpass or underpass. Or, more commonly, installing more effective safety equipment, upgrading from lights to half barriers, or half barriers to full barriers.
And are there other, maybe smaller things that make a big difference, especially for those intentional errors?
Oh, yes. Some additional measures are highly effective. For instance, physically dividing the lanes on the road approach with islands or concrete barriers.
So people can't just zigzag around the half barriers?
Exactly. That alone can cut intentional errors by up to 80%. Huge impact.
80%.
And installing cameras, red light cameras, essentially for enforcement, that can reduce those specific red light violations by up to 70%.
Enforcement and physical design changes really work. They directly lower that H factor, the hazard probability.
They do, by making it physically harder or less appealing to make those dangerous choices.
Okay, let's tie this together with an example. Can you walk us through one?
Sure. Let's use the one from the analysis. Imagine a crossing. 100 passenger cars per day. It currently just has light signals, visibility is good, and trains run at 80 kilometers per hour.
Okay.
Scenario 1. Let's say there are 40 trains per day using this crossing. You plug all the numbers into R equals EXHX the traffic volumes, the H factor for light signals, 10 to 2, the U for good visibility, 10 to 2, the S for 80 kilometers. You run the calculation.
And the answer is?
The calculated risk, R, comes out at 0.00014 weighted personal injuries per year.
0.00014. And our acceptable threshold was 0.0002.
So it's acceptable. No immediate action needed based on this calculation.
Okay. But now, scenario 2A. Same crossing, same cars, same lights, same speed. But now, train traffic doubles to 80 trains per day.
Right. The exposure factor, E, essentially doubles, recalculate R, and the risk jumps to 0.00027 weighted personal injuries per year.
So we're 0.00027. That's above our 0.002 threshold.
Correct. Now it's unacceptable. The increased train frequency pushed it over the edge.
So risk control measures are needed. What's the fix in scenario 2B?
In scenario 2B, we keep the 80 trains per day, but we upgrade the protection. We install half barriers along with the light signals.
Okay, what does that change in the formula?
It changes the hazard factor, H. Remember, light signals were 10.2. Light signals with half barriers bring H down to 10.3, an order of magnitude improvement.
So you reduce H by a factor of 10, recalculate R again.
And the risk now drops dramatically to 0.0000027 weighted personal injuries per year.
Way below the 0.0002 threshold.
Exactly. So by installing half barriers, we've taken an unacceptable situation and made it acceptable again, even with the higher train traffic.
That example really nails it. It shows how these calculations aren't just theoretical. They directly drive decisions about what specific safety equipment gets installed.
Absolutely. It demonstrates the direct link between the risk analysis and practical safety improvements.
Okay, that's choosing the right protection. Now let's switch gears to the second major application you mentioned, setting technical safety targets. This sounds like it's more for the manufacturers, the companies building this equipment.
Precisely. This is crucial for them. The goal is to set safety targets that are abstract enough to allow manufacturers flexibility and innovation in how they design their systems.
So not telling them exactly how to build it.
Right. But at the same time, the targets need to be precise enough to absolutely ensure the required level of safety is achieved. They're often set for specific functional units within the overall level crossing system.
Like the activation system or the barrier mechanism itself.
Exactly. Things like activation, supervision, the protection elements, lights, barriers, deactivation. The procedure is a bit different here.
How so?
First, you define the system very clearly and state your assumptions. You define those functional units. Then you identify the dangerous failures specifically of the technical equipment. What happens if a component breaks?
Focusing purely on tech failure now, not human error.
For this specific application, yes. The idea is to determine how reliable the tech itself needs to be. Then you establish an overall or global safety target for the entire technical system. And finally, you allocate or break down that global target into specific targets for each functional unit.
You mentioned different system versions earlier. Like using trackside signals versus remote monitoring for supervision.
Yes, the analysis might look at different architectures. For instance, System version 1 might use traditional railway signals for supervision, while System version 2 uses remote supervision from a control center. The safety targets might differ slightly depending on the architecture.
And the key assumption here.
For setting these technical targets, we generally assume the road users will respect the equipment if it's working correctly. We're focused solely on the risk from the equipment failing. And we usually make a pessimistic assumption. Any dangerous technical failure is assumed to lead directly to a hazard.
Better safe than sorry in the calculations.
Exactly, it builds in a safety margin. We then identify the worst-case technical failure, the top event, and use tools like fault trees.
Fault trees, what are those?
Think of it like a logic diagram, working backwards from the top undesired event, like crossing fails to warn of train. The fault tree maps out all the combinations of lower-level component failures that could lead to that top event, like the lights don't activate because the activation sensor failed, or the power supply failed, or the control unit failed.
So it maps out all the ways the tech could break down dangerously.
Precisely. It helps identify the critical components and failure paths.
Okay, so what about that global safety target for the technical system? How safe does the tech itself need to be?
Here we often look at general safety standards, like the CSM directive you mentioned, common safety methods. For technical systems where a failure could have catastrophic consequences, there is a widely accepted principle that the failure rate should be less than or equal to 10 to the power of -9 failures per operating hour.
10 to the -9 per hour. That sounds incredibly small.
It is incredibly small. It translates to something like one dangerous failure expected in over 100,000 years of continuous operation for a single system. It's aiming for virtual perfection in the technology.
Wow, okay. How does that apply specifically to level crossings? Are collisions always catastrophic?
In the risk matrices used, like in standard EN 50126, level crossing collisions are often classified as critical severity, potentially several serious injuries, maybe fatalities. For critical severity, the generally accepted tolerable hazard rate, or THR, for the technical system is typically 10 to the power of -8 per hour.
Okay, 10 to 8 per hour. Slightly less demanding than 10.9, but still extremely high reliability.
Extremely high, yes. And interestingly, even when we're just looking at technical failures, there's still that tiny chance of unavoidability being less than one mother. Remember, the road user might still react and avoid the crash, even if the system failed.
Ah, right, that U factor again.
Yeah. If we estimate that maybe 1 in 3 technical hazards might still be avoided, U equals 13, then the tolerable rate for the top event, the dangerous technical failure, can be slightly higher, around 3 times 10 to the power of -8 per hour.
Okay, so that's the overall target for the entire crossing systems tech.
Yeah.
Fail dangerously less often than about 3 by 10 to 8 times per hour.
How do you translate that into requirements for, say, just the barrier motor or just the flashing light unit?
That's where the fault tree comes in again. You apply that global target, like 3 by 10 8Rs, to the top event and the fault tree, and then you allocate that target down through the logic gates, A&E gates or R gates, to the individual functional units.
So each component gets its own slice of the failure budget. Essentially, yes. For example, the analysis might calculate that for the protection function, meaning the road signals failing to light up after being told to the tolerable hazard rate for that specific function needs to be around 5 times 10 to the power of -9 malfunctions per hour.
So the individual component targets can be even tighter than the overall system target, depending on how critical they are in the fault tree.
Exactly. And you might find differences based on the system design. That system version 1 with separate supervision might have slightly more relaxed requirements for some individual units compared to version 2, but the core control elements in both would still need incredibly high integrity levels.
It's amazing the level of detail and rigor that goes into this. Thinking back over our whole conversation, what really stands out to you? What's the core takeaway for someone trying to understand level crossing safety?
I think it's the sheer complexity and the structured way engineers try to tackle it. It's not just guesswork. It's about modeling everything, the environment, the tech, and crucially, that unpredictable human element.
Yeah, the human factor seems huge.
It is, and we've seen these 2 key applications of risk analysis. First, that methodical process for selecting the right type of protection for a crossing based on its specific conditions, traffic, speed, visibility.
Using R equals EX, HX, UX.
Right. And second, the process for setting those incredibly stringent technical safety targets, like the 10.8 or 10.9 per hour rates for the manufacturers building the equipment, making sure the tech itself is ultra reliable.
What about the current state? Are these methods used everywhere?
That's a really important point. These quantitative risk assessment methods, especially for choosing protection levels, are recommended because they help allocate resources efficiently, putting the best protection where the risk is actually highest. But in practice, in some places, Germany was mentioned as an example, the selection of protection measures isn't always strictly based on this type of quantitative assessment. Sometimes it's based more on, say, traffic volume thresholds or historical rules.
So there's a gap between the best available methods and what's always done on the ground.
There can be, yes. Implementing these detailed risk assessments consistently across thousands of crossings takes effort and resources. It's definitely an area where there's potential for broader application to really optimize safety investments.
Which raises a big question, doesn't it? If we can quantify these risks with such precision, if we have these sophisticated tools, how do we make sure they're actually used everywhere to make the best possible safety decisions? Not just in certain regions or for certain projects.
That's the million-dollar question, really. Bridging the gap between the state-of-the-art analysis and widespread, consistent implementation is a major ongoing challenge for the industry and regulators.
So looking ahead, what's the next frontier? What's the provocative thought for our listeners to chew on?
Well, right now, we often treat these two tasks somewhat separately, choosing the protection based largely on traffic and human factors, and setting technical targets based largely on system reliability. The real future challenge, I think, is to fully integrate them. Imagine a single, unified risk assessment procedure that holistically considers both the probability of human errors and the probability of technical failures right from the start for any given crossing. A procedure that looks at the complete picture, how humans interact with potentially imperfect technology in a complex environment.
A truly holistic model.
Exactly. Developing and applying that kind of integrated approach could give us an even more powerful understanding of the true combined risks at these critical intersections and potentially lead to even smarter, more effective safety solutions for everyone. That's the goal to strive for.